recording and start sharing my screen. So last time we have discussed until here customer satisfaction survey. We have discussed what are the various inputs. Yes, this is the improve phase only that we are doing. Improve phase. Design of experiments means it is improve phase. Okay, so let us continue from here. Yeah, my voice is a little low, but you can probably increase the volume at your end. Okay, so let us do this. Let me go to start DOE factorial and analyze the factorial design. We are providing inputs to the design of experiments. How do we provide inputs? Let me go here, not this one, this one. Okay, I need to go to stat DOE factorial, and then we need to click on create factorial design. If you want to create factorial design, you can do that, or let us analyze the factorial design. Let me actually minimize this, or let me close it. Okay, start DOE factorial, analyze factorial design. What is the satisfaction? We want to here look into the satisfaction. Satisfaction is the response. The response means Y. Satisfaction is Y. What does that Y depend on? What are the various things that this depends on? Sorry. What is happening here? Okay. Not sure what was happening. Okay. Y is the response, which is the satisfaction. Okay. Once we have the satisfaction, we need to look into the other things. For example, we need to look into the various terms that we are using, right? And then we need to look into the various graphs. So let me take you there. Terms. Let me select everything. So we have speed, factor 1. B is quality, which is factor 2. C is service, which is factor 3. Then we have two interactions, AB, that is speed, quality, right? Speed, service, and then quality, service. And then we have three-way interaction, which is speed, quality, and service. We have all these three things. Now let me click on graphs. We have Pareto, normal chart. For our ease of understanding, I'm selecting 4 in 1. When I say 4 in 1, that means histogram, normal plot, residuals versus FETs and residual versus order. Everything would appear in a single chart instead of having multiple charts. So when I click OK, so these are the various charts that get generated. But how do I interpret these charts? What does each chart mean? We'll discuss about those here. Let me put it in a slideshow mode. So what is this? Normal probability plot. It checks whether the residuals are following the normal distribution or not. If the blue dots fall exactly on this red line, then the data follows normal distribution. Here it's slightly non-normal is what I feel. Closer the blue dots are to the red line, more is the normality. Same goes with this also. Check if the residuals are normally distributed or not. How do you calculate, by the way, residual? Residual, any idea? Any guesses on how you calculate it? Okay, residual means, now whenever we build a prediction model, we predict the future, right? That predicted value minus the actual value. So today Anuj is predicting that he will get a job in Australia. That is my Y cap. Tomorrow in reality, when he goes to Australia, he will get a job. That is Y actual. So the difference between these two is residual. Third thing, so check if the residuals are random with fitted values. It's random. There is no specific order to these blue dots that are available. They are not in a particular order, right? So they are in a random direction. Last thing is, check if the residuals are random with respect to the observation order. So this is my first observation, second, third, fourth, fifth, sixth, seventh, eighth, ninth, so on and so forth. These data points do not follow any specific order. They're random. Yeah, so this is one chart. Next thing is full factorial results analysis. Look at this Pareto chart. Pareto chart of the FX compares the relative magnitude and the statistical significance of both the mean and interaction effects. These are the main effects, A, B, and C. What are the interaction effects? A, B, B, C, A, C. These are the interaction effects. Yeah. The effects have to be greater than the red line. This is the red dotted line, which is 2.13, right? The effects have to be greater than red line, which is drawn at 5% significance level. Yeah, effects are plotted in decreasing order. If you see A, B, C, B, C, C, and all, it's in decreasing order. And this reference red line is a significance based on the default value of alpha. Alpha default value, what do we take? We take it as 0.05. So in this example, if you see carefully, A, B, C, and BC, these are beyond this red line. Hence they are significant. The others are not. How to make sense of this plot, normal plot? A normal effects plot compares the relative magnitude and statistical significance of, again, mean and interaction effects. A line appears. This is the line, right? This line appears, which indicates where the points would be expected to fall if there were no effects. So let us read this and understand. If all the effects are not significant, then they should be close to the red line. So these three, yeah, are not significant. It's given here, legend also. Blue means not significant. Any point that falls far away from the red line, for instance BC, C, B, A, etc., are significant. Why? Because they're beyond this red line. These conclusions are the same as those on the previous page. So the histogram plot that we have seen and this normal plot, both are the same. And the significant effects are larger and further away from the line. Here is a third thing, right? So we also get results. So let us interpret these results and see. This is a session window which indicates the effects that are statistically significant. If the p-value is greater than alpha, then you say effect is not significant. If the p-value is less than alpha, then you say that the effect is significant. You have to interpret interaction effects first and then the main effects. What does that mean? First you will have to interpret interaction effect, three-way interaction, A, B, C. Here the p-value is greater than 0.05. What does that mean? If p-value is greater than 0.05, that means it is not significant. So you will try to remove this first. Right, so let us see what happens. Okay, so what have we done? We have removed A, B, C. Why did we remove this A, B, C? Because this was showing us this one. This p-value is showing us greater than 0.05. If it is greater than 0.05, then that means it is not significant. If it is not significant, you remove it. You remove it and then you again do the analysis. Once again you do the analysis. Right, again when I do the analysis, now I go and look into two-way interaction. First I looked into three-way interaction. I found that it was not significant, so I've removed it. And then I've rerun this design. When I've done that, this time I'm going to look into my two-way interaction. The p-values for both of these two is greater than 0.05. These are also not statistically significant. So you need to remove these the next time. Right? Or your null hypothesis says there is no lack of fit. Alternate hypothesis says there is lack of fit. The p high null fly. So you're going to accept null hypothesis which says there is no lack of fit. Next time what did I do? I have removed those two. I have removed these two. Because for these two, p-value is greater than 0.05. I have removed those two and then again I have run the model. This time I do not see that there is something which is not significant, that is not appearing here. All these terms that are appearing here, the p-value for everything is less than 0.05. If it is less than 0.05, what do we conclude? These values, which is speed, quality, service, and quality service interaction, these are all significant. This is the final DOE model. You do these things, you keep dropping the values until you see that there is no p-value which is greater than 0.05. Yeah. What is this lack of fit value here? P-value for lack of fit indicates that there is no lack of fit because it's greater than 0.05. And these two already we have discussed. Or null and alternate hypothesis for lack of fit. Alright. Let us look even into our R-squared value. R-squared adjusted indicates that the fit is very good. R-squared and R-squared adjusted represent the proportion of the variation in the response data explained by the model. What amount of variation in Y is explained by this prediction model? Now this adjusted R is a modified version of R that accounts for the number of terms in the model. For example, as in how you increase the number of x's, x1, x2, x3, x4, so on and so forth, right? The interaction between these, like x1 and x2, x2 and x3, x3 and x4, x4 and x2, the interaction among these variables is not explained by R-squared alone. Hence, what do? You not look into those interaction effects also, you look into R-squared adjusted. And this is useful for comparing models with different number of terms. Yeah, suppose you build two models, for example, you have built two prediction models. Right, for one prediction model, the R-squared value is showing a 60%, for example. Another R-squared value, it is showing as 90%. Which one is good? There is a general thumb rule, right, which we have already discussed in analyze phase and in Greenbelt also, that says that 0.85, right, or 0.8. Some books say 0.8. Minimum is 0.8, right? If it is 0.8 means 80%. If the R-squared value is greater than 80%, that means the model is fit. You can use the prediction model to predict the future or to predict the Y. Here is the equation that we get out of this Minitab output. This is the model equation. We want to measure the satisfaction level, and this is the equation that I'm getting. If you see carefully, there is only quality and service interaction term. There is no interaction term for speed, quality, or speed and service. Why don't we have these interaction terms? Because those were not significant. And also the three-way interaction, which is between speed, quality, and service, these are also not there. Why is this also not there? Because this was also not significant. Why? Because p-value was greater than 0.05. Yeah, so from now on, if people are going to give me the value of speed, quality and service, I'll be easily able to explain what is the level of user satisfaction. Yeah, with what speed I have to work, with what quality I have to work, and how should my service be for a particular customer satisfaction score. So that is my final model. Let us look into few graphs as well, because we can also visually analyze design of experiments. So let me go back. Let me go to stat DOE factorial plots. Yeah. So that is where we are, speed, quality, service, only model, graphs. Let me go to graphs and also select the means effect. Okay. So this is the graph that I'm getting. So here it is. Let us interpret this graph as well. The mean effect is present when the change in the mean response across the level of factors is significant. So in short, here it is very steep. The slope is very, very steep. And steeper the slope, better is the impact on the satisfaction. So it's something like y satisfaction is equal to speed, which is x1, right? And quality, which is x2. And it also depends on service, which is x3. We have 3 x's and 1 y. Here if you see speed, the slope is very steep. So it has the biggest impact on satisfaction. That is what you conclude by looking into your mean fx plot. Okay, next, you can also visualize other factorial plots. You can also visualize the interaction effect by just including those two terms. I'm including just quality and service. I want to see how to gauge the level of impact that this interaction effect is going to have. So when I plot this, here is what the thumb rule is. If the lines are parallel to each other, then there is no interaction. So this means when the quality is poor, the increase in satisfaction for increase in service is not as much as when the quality is good. That is what we can infer. If the lines are not parallel to each other, then there is an interaction between the two variables, because if the lines, if they are like this, they are parallel. If they are like this, then also they are parallel. But if there is a slight difference like this, then somewhere it's going to interact, right? Then you can say that yes, there is an interaction effect. Hence, lines should not be parallel. And the last thing is cube plot. It is used to show the relationship between factors and the response variable. What is a response variable? It is y. What are the factors? These are x's, x1, x2, x3. In our case, we have 3 factors or 3 inputs: speed, quality and service. We are measuring the satisfaction. Each cube can show 3 factors. If there are only 2 factors, then a square is displayed. Yeah, so if you have 2 factors, then it will appear like this, your cube plot. Only if you have 3 factors, it will appear as it is appearing in the diagram. It will appear like this. Yeah, these values are average of your response values. For example, if the speed is increased, then the satisfaction values increase the most. That is what you can conclude. All right. So we have a few more plots called as contour and surface plots. So how do we show that? It is, what are these plots used for in the first place? This contour and surface plots are used to help visualize the response surface. Why? We want to visualize the why. It is useful for establishing desirable response values and operating conditions. Points that have the same response values are connected to produce contour lines. So let us deal with this and let us plot it and see. So you just need to navigate, go to stat, DOE, factorial and contour plot. Let me do that. Stat, DOE, factorial, contour plot. Yeah, so you just need to click on contour. These are the things that are already mentioned here. You can go to settings, services for, you can do all of these things and just click on OK. It will produce this contour plot. Let us interpret this diagram. What does this diagram mean? So this says that the text factors, text means here in service poor or great is a text, it's not a numerical value. Text factors cannot be varied between different levels. Yeah, so if you mention the service as poor, good, etc., you cannot vary it between different levels. These are the various levels that are available. Yeah, you can use the brush symbol which is available in Mimi tab to actually select the optimum value. What is the optimum value that is required? And here is one practical example, 3 Romeos and Juliet. It is very famous example which is given by Ravinder Kare, right? So one factor at a time. Let us look at this. Run 1. There are 3 people, Ravi, Naren and Deepak. Reena winks, right? In run 2, they have removed Ravi and they have checked whether Reenu still winks or not. She again winks. They've removed Naren and they have checked. She still winks. They've removed Deepak. Reenu is not winking. Right? They've removed Ravi and Deepak both. She's not winking. Right? They have removed Naveen and Deepak. She's not winking. So that means clearly Reenu likes Deepak. This is one factor at a time. This is how we do experiment, right? One factor at a time. And that is what we think. Now what they have done, they have just introduced Deepak. Again, Reenu is not winking, but it's contradicting with this run 4. So what is happening? Who does she like really? We really don't know. Does she like Ravi and Deepak both? Yeah, we don't know. So this is one factor at a time experiment. But in design of experiment, what do? You run multiple runs to actually figure out on who does she really like. Right? When is she winking? We have Deepak here, she is winking. Here also we have Deepak, but she is not winking. But sometimes accidentally, she might not have winked, right? When you're doing that. But when you do multiple runs, again, you can straight away conclude that whenever Deepak is available, she is winking. So in one factor at a time, sometimes you might lose interesting insights, right? Because of oversight, etc. But in design of experiment, you can get rid of such oversight. Okay, so I'll just stop here.